Hi, my dear students. Today we will learn about surface charge and force on surface charge. In our previous classes, we learned about electrostatic boundary conditions and properties of conductors. There we see that there is no electric field inside a conductor. Okay? Electric field inside a conductor is 0. Okay, inside a conductor is 0. Okay, now consider a conductor and there is a surface charge on the conductor of sigma. Okay, surface charge density sigma. Now, the electric field inside the conductor is 0. Okay, let there is a surface charge density sigma on the conductor. Okay, sigma on the conductor. But we learned that electric field inside the conductor is 0. Okay. Now, what should be the electric field just outside the conductor? That is the question. Okay. So, you can find out the answer using the electrostatic boundary condition. There you see that electric field above minus electric field below is equal to sigma by epsilon 0. And already we see that electric field below, because electric field inside is 0. So the electric field just outside the conductor is sigma by epsilon 0 n cap. Okay. So the electric field just outside the conductor is given by electrostatic boundary condition. Okay, electrostatic boundary conditions of electric field. Okay, electric field. So what is then? That means the electric field just outside the conductor is given by sigma by epsilon 0 n cap. Okay. Now you know that once you know the electric field, you can find out the surface charge density sigma from this expression. Okay. Similarly, we learned about the boundary condition of potentials. There you see that sigma by epsilon 0 equal to minus dou V by dou N, where V is the electrostatic potential. Okay, so if you know the electric field or the electrostatic potential, then you can find out the surface charge density sigma. Okay, so once you know the electric field and potential, either electric field or potential, we get a knowledge about the surface charge density sigma. Okay, now we can think about what is the force on this surface charge. Okay, that is the next question. So just remember all these things. Here we just use the boundary conditions. This is from boundary condition for electric field and this is from boundary condition for potential. Okay, either using this expression or this expression, you can find out the surface charge density. Okay, now we can derive the expression for the force on surface charge. Okay. Now, the force on surface charge. Surface charge. We already assumed a conductor whose surface charge density is sigma. Okay. Now, what is the force on this charge, surface charge sigma? We can call it as force per unit area because this charge is charge plus charge per unit area. Sigma is charge per unit area, surface charge density. So, you can define the force small f as force per unit area. Okay, force per unit area. Okay, then this F is equal to sigma E. Okay, the force per unit area on a surface charge sigma is given by F equal to sigma E. E is the electric field. Okay, now the question is, we already learned that electric field is discontinuous on the surface of a conductor. Okay, so what electric field do we want to use here? That is the question, because there is an electric field below the conductor and the electric field above the conductor. Both these electric fields are discontinuous by an amount sigma by epsilon 0. Okay, so we have to use here the electric field. What is the electric field we want to use here? That is the question. Okay, here we use the electric field as average value of the electric field, E average. Okay, this E average is given by electric field above plus, okay, electric field above plus electric field below divided by 2. Okay, that means this F equal to sigma E average. Okay, force per unit area on a surface charge sigma is given by F equal to sigma E average. This is equal to sigma by 2 into electric field above plus electric field below. Okay, electric field above plus electric field below. This is the force per unit area. Now we want to find out how we can conclude that this is the field we need here. That is the question. We want to find out this E average. How we get this expression. For that, just consider a surface charge like this. Okay, this is a surface charge density and there is a patch here. Okay, in this patch, the electric field above this patch is given by sigma by 2 epsilon 0, and the electric field just below this patch is also given by sigma by 2 epsilon 0. Electric field below and electric field above are discontinuous by an amount sigma by epsilon 0. We already learned about this. So these are the electric field due to a small patch. Now the question is, suppose this is the n cap vector. N cap vector is normal to the surface. Okay. Now suppose that we want to find out the force on this small patch. Okay. We know already we learned about the force acting on a body. No force can act a body itself. That means the force on this patch is not due to this patch but due to the outside surface charge. Okay, that means the force acting on this patch is due to the electric field of the other charges on the sheet. Okay. Similarly, if a patch of surface charge is there, we can't find out a force acting on the surface charge due to the charge itself. Okay. The force acts on this patch due to all other charges outside the patch. Okay. So there is an electric field here like this. Okay. There is an electric field here like this. We can call it as E other. Okay. E other. This E other is the electric field on this patch due to other surface charges. Okay. Outside this patch. Similarly, here is also there is a electric field due to other surface charges. Okay. The electric field above this surface charge distribution. Okay. Electric field above can be written as sum of two terms. That is, electric field due to the surface charges outside this patch, which is represented by E other. Okay, E other plus electric field due to the surface charge on this patch sigma. Okay, this patch is given by, this electric field is given by sigma by 2 epsilon 0 n cap. Okay, sigma by 2 epsilon 0 n cap. We assume this patch a very small, tiny patch, such that the surface charge distribution is almost constant over this patch. Okay, and on this patch, the electric field contribution is above this patch is sigma by 2 epsilon 0 n cap. We already learned about this. Okay, and now E other is the field due to all other surface charges. Okay, that is E other. So this is the total field above the surface charge. Okay, now above the surface. Now similarly E below. Okay, E below is given by electric field due to all other charges plus, sorry, not plus, this time minus, because this aerial vector pointing downward. Okay, and so there is a minus sign, and minus sigma by 2 epsilon 0 n cap. Okay, these are the expressions for E above and E below. Okay, now if you add these two, E below and E above, you can see that this contribution cancels out. Okay, and so this gives us E above plus E below equals, when you add these two terms cancels out. That is, the contribution due to the patch cancels out, and you get here 2E other. Okay, so the force due on the patch is due to all other surface charges outside the patch. That is the concept here. Okay, so the field due to all other surface charges is given by this E other, and so E other is given by 1 by 2 E above plus E below. This is E average. Okay. This is E average which we have written here. Okay. That means the force on a surface charge sigma is given by the average, the force on a surface charge distribution sigma is given by the expression sigma E average. Okay, that means this E average is given by half of E above plus E below. Okay. Now we can rewrite this expression. Force on this surface charge density sigma. Okay. F is equal to sigma by 2 E average. Okay. And now we know that this E average in the case of this sigma into E average, not sigma by 2 E average. Here we write this expression as F is equal to sigma into E average. Okay. And in this case, in the case of a conductor, we know that electric field below the surface inside the conductor is 0 and electric field just outside the conductor is sigma by epsilon 0. So you can replace this with that expression and so you get here sigma into sigma by epsilon 0 plus 0 by 2. Okay, this is the average value and this gives you half sigma square by epsilon 0. Okay, this is the force on the surface charge density sigma and this directed along the n cap direction. Okay, normal to the surface. Electric field is directed normal to the surface. Now you can think about the pressure on the surface. Okay, the pressure, radiation pressure. Pressure on the surface is given by force into area. Okay, this is given by this force. Pressure is given by force into area. Here we written this force as force per unit area. Okay, and so you can write this pressure as a substitute for sigma. That means you can write here half epsilon 0 into, we already know that electric field is equal to sigma by epsilon 0 here. Here sigma square. So you can write here E square epsilon 0 square. Okay, from this expression. So you get here epsilon 0 E square by 2 for the radiation pressure. Okay, epsilon 0 E square by 2. Now you think about another thing. We already learned about electrostatic energy. Okay, there you see that the electrostatic energy, we use the same notation E, electrostatic energy. Okay, electrostatic energy equal to epsilon 0 by 2 E square d tau. Okay, and this term half epsilon 0 E square by 2 is called energy density. Okay, energy density is equal to epsilon 0 E square by 2. Okay. Now the radiation pressure is also obtained as epsilon 0 E square by 2. Okay. The radiation pressure on a conductor is given by the same expression epsilon 0 E square by 2. Okay, so in this section we discussed about how to find out the surface charge density. If you know the electric field or the potential, you can find out the surface charge density using the boundary conditions. Okay, similarly, you can find out force on a surface charge distribution, and it is given by the expression sigma force is given by the expression half sigma square epsilon 0, which is oriented normal to the surface. Discuss about capacitors. Okay. Consider two conductors having opposite charges. Okay, having equal and opposite charge. Charge Q and minus Q. Okay, then the potential difference between the conductors, as all of you know, the potential on a conductor is always a constant. Okay, potential on a conductor is a constant, and here the potential difference between the conductors. Okay, potential difference between the conductors. Right here PD. Okay, potential difference between the conductors. You can write it as V. This is equal to V plus minus V minus. That means potential of positive charge minus potential of negative charge. And I can write this as minus integral minus charge to plus charge E dot dl. Okay, this is from the definition of the potential. You can write this expression like this. Okay, and now from this expression itself, if you substitute for electric field, you can see that this electric field is proportional to charge Q and electric field is proportional to potential V. Okay, electric field is proportional to charge Q and electric field is proportional to potential V. That means you can write this proportionality constant Q by V equal to a constant which is called as capacitance. Okay, this is called as capacitance. The electric field is proportional to charge Q and similarly electric field is proportional to potential. So the ratio between this charge and potential is also a constant. This is called capacitance. Okay, this is measured in units farads. Okay, we use the unit farad. Farad is the unit. Okay, for potential capacitance is measured. The unit is farad. Okay, and we call this unit as microfarad or picofarad, etc. Okay, microfarad means mu f. Okay, microfarad means 10 raised to minus 6 farad, or picofarad is 10 raised to minus 12 farad. Okay, these are the units. So if two conductors separated by equal and opposite charges can act as a capacitor. Okay, whose capacitance is given by this expression Q by V, and its unit is represented by farad. Okay. Work required to charge capacitor. Okay. Now, suppose some intermediate stage, the potential difference of the capacitor. Okay. The potential difference between the conductors at an instant is given by Q by C. Okay. Now, if you want to charge the capacitor, it means that you move charge Q from positive conductor to negative conductor. You have to do work against the electric field. Okay. And now, this work done to take dq charge from positive plate, okay, from positive conductor. dW equal to potential is given by Q by C into dq. Okay, and now the total work done to charge the capacitor is given by W equal to integral 0 to Q dq by C. Okay, C is given by the capacitance, and so this is equal to half Q squared by C. Okay, so the work done to charge the capacitor is given by the expression half Q squared by C, or you can write this as, you already learned that Q by C is V half Q by V. Okay, or you can write this Q as C into V, so you get here half CV square. Okay, this is equal to half CV square. Here this V represents the potential difference between the two plates, the final potential difference between the two plates. Okay, these are all about electrostatics. Hope that you can understand the concept very well, and so learn well and do more problems to clear the concept in perfect manner. Okay, thank you.